Hello friends, welcome to Vishwanath Academy YouTube channel. I am Rahul Saha, I am the NEET faculty and today we'll be talking about the urinary system and I'll be bringing to you the lecture about the nephron. As you might have been knowing already that nephron is the fundamental unit of a kidney. Each kidney contains, you can say, almost 1.25 million nephrons. This is a diagrammatic representation of a nephron. A nephron can be divided into renal, corpuscle, and renal tubule. Renal corpuscle is again divided into glomerular capillaries and the glomerular capsule, also known as Bowman's capsule. The renal tubule, in turn, is divided into the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule. Then it further becomes collecting duct, then it becomes the renal papilla, then minor calyx, then major calyx, then the renal pelvis. Now, in this lecture, we'll be digging deep into the structure of the glomerulus and how does one specific filtration process occur through glomerulus. Now, as you can see here, this is the cortex part of the nephron, this is the medullary part of the nephron. Now, the cortex is the outer region, medulla is the inner region of the nephron. What happens is this specific nephron is a juxtamedullary or medullary nephron. I would like to tell you one thing that the cortical nephrons are 80 to 85%. They are more numerous compared to the juxtaglomerular or the medullary nephrons. They are only 10 to 15%. What really demarcates and differentiates a juxtaglomerular or a juxtaglomerular and medullary regarding, or you can say comparing it with the cortical nephron, is the presence of the thick ascending limb. You can see this one. This is the thick ascending limb. This one is the thick ascending limb. We also call it or abbreviate it with TAL. TAL is only present in case of juxtaglomerular nephrons or medullary nephrons. They make them longer. These are the longer nephrons. So you can see the long nephron loop. And what demarcates a TAL from a thin ascending limb is that in case of the TAL, suppose this is a TAL and this is the thin ascending limb. You can say this is thin, this one is the thick part. Now, what is the main difference? The main difference is we'll be having cuboidal epithelial cells, low cuboidal with little bit of microvilli, and here it will be squamous epithelial cells. So the lumen diameter, if you compare of the thick ascending limb and the thin ascending limb is almost the same. But the thick ascending limb is only permeable to solutes. I'll explain to you in the later lectures that it contains a specific receptors known as Na plus K plus 2Cl minus importer. Is only present in thick ascending limb. And only this nephron takes part in countercurrent multiplication mechanism. The thin ascending limb are incapable of doing so. Now, if you come to the renal corpuscle, what I'm trying to show you here is you can see that the glomerular capillaries, what kind of capillaries are they? These are fenestrated capillaries. Getting the point? Fenestrated. Because capillaries are of three types. They are continuous, they are fenestrated, and they are sinusoidal. Here, there is gap between the two endothelial cells, and the diaphragm is also quite loose, but the basal membrane doesn't have much gap. So why do we need fenestrated capillaries in kidneys in order for the filtration to take place? What I would like to show you here is there is a conceptual, you can say, anomaly that you might have encountered in other lectures. Like when I was a student, I used to think that suppose this is the afferent arteriole. Suppose this is your afferent arteriole. This is your efferent arteriole. And this is the, suppose here you have a lot of glomerular capillaries. Now you might be thinking that these are the capillaries, then all the blood is getting filtered. The concept is absolutely wrong. What happens is you have something known as GFR, and you need to know what is renal plasma flow, and you need to know what is the filtration fraction. The filtration fraction is only 20%, meaning that we know that the cardiac output which is coming to the kidney is 20 to 25%. Let's suppose it is 1.2 to 1.3 liter for your simplicity. Let's suppose 1 liter of blood is reaching kidney per minute. Just for your simplicity, 1 liter will have 400 ml cells, RBC, erythrocytes, leukocytes, macrophages, all those cells, and 600 ml will be plasma. The plasma is the thing that will be filtrated, or that will be filtered. How much of the plasma is filtered? Only 20%. Meaning that 20%, if you take out of it, you will get 120. So 120 is the glomerular filtration rate per minute, and what you have left is 480 ml. 480 ml will go here. That won't be filtrated. You'll be asking the question why? Because if everything is filtered out, this is carrying HbO2. So the other parts of the kidney will never get HbO2 and they will die via necrosis. Direct necrosis will happen. And in this case, necrosis will not happen. They will also get HbO2. And if you notice one more thing here, this is a high pressure system. If you know about hemodynamics and the body, then you might be knowing that wherever a capillary bed is present, it is fed by a met arteriole or an arteriole and it is drained into a venule. Venules are the low pressure system. So it is high pressure to high pressure. It is again an exception. Why? Because this will send blood, efferent will send blood, oxygenated blood to the peritubular capillaries and then it will drain into the venules, the cortical radiate veins, arcuate veins, and so on. So get that concept very, very clear. So only 20% is filtered. The filtration fraction is 20%. So I can say filtration fraction FF is glomerular filtration rate upon renal plasma flow. You can say like that. Then glomerular filtration rate 120 upon, you can say 600. So like that, you can definitely find out the value. Now, coming over here, what we see over here is we see the parietal layer, the visceral layer, the podocyte. So specifically what happens in a nephron. So what we know is the nephrons are also, or the glomerulus specifically is also interdigitated, it's surrounded by mesangial cells or Pulkison cell, or they're also known by the name Lasix cell. Now, mesangial cells have multiple functions. Mesangial cells can do what? Mesangial cells can control GFR. They also have receptor for angiotensin 2, which will make them to contract and decrease GFR. If they relax, GFR is increased. They also are receptive to atrial natriuretic factor or peptide secreted by the left atrial wall of the heart. Now, in this specific arrangement, how does the filtration really take place? That is the question here. So what you can say is, this is the filtration slit. So I'll draw a mini filtration slit here and try to explain. You can have, or you can visualize it. Filtration slits are made up of podocytes. What you have is, you have multiple glomerular capillaries going on. Multiple glomerular capillaries going on. You can think like that. And then what you can do, you also have something known as the basement membrane. You have something known as the basement membrane. And then you have cells like this. This is the visceral epithelial cells which will become parietal epithelium, and then it will become simple, you can say, cuboidal epithelial cells with microvilli that will become PCT. And this side is your glomerular capsule. Now these cells are visceral epithelial cells which you can see here as well. And these foot processes are known as the podocytes. First of all, these capillaries are fenestrated, as we have seen in the previous slide. Now, what is the diameter? The diameter of the fenestra or the holes is 70 to 90 micrometer. Now, not a single cell can pass through this diameter, but albumin can surely do, which is the maximally rich protein in the blood. Albumin, globulin, fibrinogen. Albumin is the smallest and is present in maximum amount. Its diameter, albumin, is 7 to 8 nanometer. And this is also nanometer. So 70 to 90 nanometer is the diameter of the fenestra. 70 to 90 nanometer is the diameter of the fenestra present in the fenestrated capillaries, which are also known by the name glomerular capillaries. And the diameter of albumin is 7 to 8 nanometer. Now, albumin will rapidly pass through, and then it will come into the capillary space. Through PCD, we can only reabsorb amino acids, not the complete protein like albumin. Then albumin would come in urine. We will be having albuminuria, also known as proteinuria. That would cause pedal edema and then bilateral edema and ultimately death. So that we see in patients suffering from chronic kidney disease, where the EGFR falls, the proteinuria rises a lot. Right? So that happens due to certain pathological conditions like glomerulonephritis, okay, like pyelonephritis, minimal change glomerulonephropathy, okay, hereditary nephropathy, Good-Pasture syndrome. There are so many pathological conditions which we'll touch upon later on. So here, these cells are also covered by negatively charged molecules like cyanoamino groups made up of sialic acids, cyanoaminoglycan group. And then this is the basement membrane. If you know about basement membrane, it is acellular. It has lamina lucida and lamina densa. It is made up of a lot of fibronectin, proteoglycans, which are again glycosaminoglycan plus protein. Glycosaminoglycans are again heparin sulfate, keratan sulfate, dermatan sulfate, hyaluronic acid, and it is also made up of lidogen or intactin. Collagen type 4 is present here. So it has got a lot of negatively charged proteoglycans. So they also make the charge negative. Here also you have sialoglycoproteins. They make the charge negative. And proteins, if you know, are also negatively charged. So hence there will be a lot of repulsion. So what we are trying to do is we are trying to impede. We are trying to impede the flow of albumin. In the end, even if some albumin comes through due to the hydrostatic pressure that we'll be talking about in the next video, and also coupled with that BCOP and capsular hydrostatic pressure, the next filtration pressure that will be covered in the next video. So what will happen is these are known as podocytes and they are having some foot processes which are known as filtration slits. So you can imagine it like this. The foot processes are like this. Just imagine. So they interdigitate. So the holes become smaller or the fenestra becomes smaller and smaller. So this is the purpose of the foot processes, the interdigitation. Now, in the new medical books, you will see filtration slit. The filtration slit is nothing but you have a slit here as well to even impede it. This is known by the name filtration slit and it is made up of the protein nephron. Now, effective diameter in the end becomes how much? 7 to 9 nanometer again, or 0.007 to 0.008 micrometer. Now, albumin and the diameter becomes equal. Now, albumin cannot pass through because they are being impeded by negatively charged proteins and proteoglycans as well. You will be having virtually no albumin. But in the real case, we will be having some albumin, but we take medically, clinically, that virtually there is absence, the absolute absence of albumin in the capsular space. All the albumin is trapped here only and it stays in the circulation. And hence it maintains the hemodynamics. It prohibits the formation of edema in the vascular system, in the systemic circulation. So this is the specific route that is followed by the glomerulus. And this is surrounded by all the sides through mesangial cells. So by mesangial cells could be your intraglomerular, could be extraglomerular. Mesangial cells secrete something known as, you can say, mesangium. Mesangium is a connective tissue layer which will bind on to entire glomerulus. Then it is known by the name glomerular tuft. Now, what mesangial cells can do is, I told you earlier also, they can regulate the GFR. Contraction increases, relaxation will, you can say, contraction will decrease GFR. Relaxation would increase GFR. And then they are also phagocytic in nature. They also function as macrophages and clear the debris and of harmful pathogens. The same basal membrane thing has been explained in this diagram as well. And you can see here the fenestra length is there, and then we have the capillary, we have the podocytes, we have the foot processes, and one more thing you should know is the presence of nephron, which will impede, or which is the filtration slit, or which ultimately impedes, or which is the final embodiment of impediment for the albumin. So it completely impedes the filtration of albumin and prohibits the albumin from coming into the capsular space or into the Bowman's capsule or into the glomerular capsule or the glomerular space. So that's it for today. I hope you like the content. If you want to be a very, very avid learner and keep following the lectures, then do hit the subscribe button and the like button, and please share with this video with all your friends and stay tuned for my later lectures. Thanks a lot. Have a nice day.